Okay, so we saw the fundamental problem with being able to prove anything about the worst case behavior of hashing. And so I want to try to move beyond the approach that I've shown you to this point and add a simple little twist that's going to allow us to do a little bit of theoretical work. And it's going to lead to some approaches that in practice allow us to say something concrete about the performance of hashing. Okay, and the idea is to add randomization. But when we say add randomization, of course, we do not mean add randomization to the process of producing the hash value from the object, because again, that's not going to enable us to look it up once we've stored it. So the idea is to use randomization in the construction of the hash function, although the hash function H itself will still be a deterministic function. I'll explain what I mean in a minute. If we do that, we can guarantee that for any sequence of insert and lookup operations, if we randomly choose little h from a family of hash functions, then the performance of h on the sequence of lookups and insert operations will have certain properties in expectation. In particular, will have the property that we were seeking of the uniform hash function, but this will be in expectation. So it's actually quite subtle. And something that works well in expectation is not necessarily going to work well in a given realization. And so we have to make a little subtle twist at the end in order to be able to say some concrete things about how things will actually work in a particular realization of probabilistic um, set of operations. So I'll explain in more detail in a minute. But this is the idea of universal hashing. So let me try to add some substance to that by giving a definition. Okay, a randomized algorithm, this is definition 10.1 because it came from another place that I wrote it. A randomized algorithm H for constructing hash functions little h that map from U, the universe of keys, to the hash bucket list 1 to capital M, which is the same terminology we've been using to this point, is said to be universal if for all pairs of keys X and Y, where X and Y are not equal in the universe U. Okay, so this is going to be true of each pair. It's important. This is a subtle definition. And it's not true for triplets or quadruplets. It's true for each pair. Okay, that the probability, if we select a little hash function H from a family of hash functions, capital H. So I made that shift kind of quickly. So I should emphasize that the universal hashing is based off of a family, capital H, of hash functions. There are a lot of them, or even possibly an infinite number of them. And we are going to randomly pick, in order to start hashing, a particular hash function, little h, out of the family of hash functions, capital H. Okay. Now, it is defined as a family of hash functions. I'm sorry, it is defined as a universal family of hash functions if it has this property. Okay, if when we choose a hash function from that family randomly, that all pairs of keys only have at most a 1 over m chance of conflicting, where m is the number of buckets in the underlying hash table. Okay, so that's very subtle. Let's think about what that means. If we pick any two keys randomly, and we then select hash function little h from h, only 1 out of m of the times that we do that are those two keys going to conflict. Okay, that's one way to look at it. So pick two random keys that you want to hash. I mean, any two keys. It can be random, or you can just select them for some particular reason. But when you pick a little h from capital H, there's a very good chance that they're going to hash to different places. In fact, the chance is at most 1 over m, where m is the number of buckets. So I'm going to make this concrete by building such a family. And I wrote a little code that shows you exactly what that means. But I think it might be pretty clear just from the statement of this definition, but I think it'll be clearer when I actually show the example. Okay, so that leads to a very important case, which you prove just based off of the linearity of expectation, which is that if H is a universal family of hash functions, then for any set of keys S that are drawn from U, the universe of size n, for any given key X in U that you might want to look up, for example, if we construct H at random from the family H, so we say construct because there might be an algorithm to build it, or we might think of there just being a set of hash functions, capital H, that we randomly choose a little h from, then the expected number of collisions between X and all the other elements of S is at most n over m, which gets us exactly where we want to be for our situation of ideal uniform hashing, right? So that's just a consequence of the less than or equal to 1 over m property for pairs. Okay, and we have to ask the question, why do we care about the expected number? That's a very good question. And you might not, but I'm going to be able to make the leap from expected to actual behavior and practice, even if it's not, even if it requires some additional assumptions that might not be exactly the ideal situation in terms of either how much memory that we have to allocate to achieve certain things. So I'll explain in a minute. But anyhow, it's important to realize that that is still a leap because we're talking about in expectation. And the proof of this is just based off of the linearity of expectation. We say if we let this quantity C of xy equal 1 if x and y collide and 0 otherwise, and we let C of x denote the total number of collisions for a particular key x, so that C of x is the sum over all y not equal to x of all the keys in the set, then summed over y, then we know that the expected value of C of xy is just less than or has to be less than or equal to 1 over m. Okay, and so if you then sum them up, you find that the expected value of C of x just has to be less than n over m. Okay, so if we think about that, that just means that the probability of conflict of this key with all other keys in the set has to be at most n over m, right? That's exactly what we were looking for. And I think it will be more concrete when I show you an example, but that's the basic idea, okay? And there's an important corollary that comes from that, which is exactly what we want to achieve for hashing. And that, so H is one of these families of universal hash functions. And we want to do any sequence L of insert, lookup, and say even delete operations. And we're looking at only m elements at a time, where m, again, is the size of the underlying hash table, right? So whereas the most conflicts we could get was n over m, now we're just looking at m elements at a time, then we can guarantee that the total cost of the L operations for random choice of little h out of h is going to be order L, okay, assuming that we make standard assumptions about constant time for computing the hash function h. Okay, so that's exactly the idea that we're going for. The twist here is that it is the expected total cost. Again, that does not mean if you do this process by picking a random h out of capital H and you start hashing that you are guaranteed to have order L operations for m elements in the table. That's not what it means at all. Okay, so you have to think about that. It could still be the case that you have all conflicts and you all hash to the same bucket, but in expectation, that's not true. Okay, so in other words, the probability of that happening is less than the probability of any conflict between any two keys is less than or equal to 1 over m. Okay, so how are we going to turn that into a useful statement? Well, we'll see, but for now, at least we have a theoretical statement, an expectation that is more than we had without adding randomization in the concept of a universal hash family. So we'll look at that next. We're going to build a universal hash family based off of something called the matrix method. And I'm going to show you what it really means for the probability of conflict between any two keys to be less than 1 over m. Okay, because we'll actually randomly choose from this family and we will see which members of the family cause a conflict. And then the last step, we'll try to turn that into a useful statement about how hashing can, in practice, guarantee certain bounds on performance.